It's recording.
Okay, good. Science time, physical science time even. You guys now are in physical science, so physical science time. Let's erase this Latin. Today we're talking about, it's more than just this, but let's label this lesson Newton's second, I'm going to put in parentheses, and third law. Well, that was confusing, and the reason I did that way is because depending on how much time it takes to talk about the second law, if I remember correctly, well, I do remember one thing distinctly. When I did this lesson last year for your friends, the freshmen from last year, I did this lesson for them while they were all at home because one of them got the corn virus and they all had to stay at home, and so I did this online for them. In fact, this is why I started filming the lessons. But, like I say, that I'm pretty sure when I did that lesson last year, I did all of this in one, and it took about somewhere between 25 and 35 minutes, which would be fine. But depending on how far we get, we may talk about the second and the third, or we may just talk about the second. So let's get started. Remind me first, before we go much further, these two things being named this very heavily implies that there's another thing named what? That we've already talked about.
First law?
Newton's first law. And what is Newton's first law? Let's write that first. Newton's first law. Someone remind me what that was.
Inertia.
Okay, hold up. First, let's just do inertia first, and then we're going to write another colon, because it is, this law describes inertia in most of its fullness. The only thing it kind of omits is that this does depend on the mass of the object, but it's more elegant if we tell it the way that Newton said it. He originally said it in Latin, which that is not what the Latin was on the board, but it was the same language. What is the English translation of what he said in Latin in his book Principia Mathematica?
So lazy.
No, you're right. The word inertia means lazy as a translation, but I'm talking about the law itself, which he would have originally written in Latin. What is it in English, Justice?
An object in motion will stay in motion, and an object will stay at rest unless acted upon by an unbalanced force.
Thank you. Justice sighs.
I'm tired.
An object in motion will stay in motion. I'm going to parenthesis it up here. What should I put in the parentheses describing the specific motion of that object? Yeah. Constant. You said speed, but there's another part of it, so let's call it instead constant velocity. That means it has to have the same speed and direction. So an object in motion will stay in motion, and an object at rest, that one we don't need a parenthesis for, will stay at rest unless acted upon by an unbalanced, I'm going to put another thing in parentheses here, force. What's going to fit in those parentheses that also describes unbalanced? What do we call the total force acting on an object? Net force. And if the net force is non-zero, then it's an unbalanced force. Well, let's just put non-zero net force. If I had known that
So my pen exploded a little bit.
That's good. Go sit down. If I had known that we were going to be talking about it specifically, I would have gone to the trouble to memorize the Latin so we could write it up here too. But you're not interested in that. It's probably a waste of my time. I am interested in it. I think it's cool. Sounds like a magic spell. Probably. Like I said, I didn't memorize it, but it would have originally been written in Latin. This is Newton's first law. Do you remember from last year or maybe another time in your life what Newton's second law is? That's what we're talking about today.
No.
Friction. No. It can have to do with friction. Newton's second law. You probably remember the third, but we're not going to talk about that one yet. It was one of your vocab words. You really should remember from that. Yeah, right.
How much force you apply on something, it applies as much force on your back.
That's the third law. We're going to get to that. Leo?
Newton's second law of motion, the acceleration of an object in the same direction as the net force on the object.
Yes. Acceleration and net force are proportional and act in the same direction. Semicolon. Mass and acceleration are inversely proportional. We had one word to describe Newton's first law. What was it? Inertia. We have an equation to describe Newton's second law. Does anyone remember what that is?
Is it
Oh,
A
equals
delta V over...
That's the equation for acceleration if we have velocity and time. You're thinking of A equals delta V over t, which is true. That's one way to solve for acceleration. Anyone else remember? Yes?
What's it? A equals V sub f.
That's the same thing as what he said.
Yeah.
But this one is, let me give you the first letter. F equals, you remember now?
Oh.
We did this last year.
Mass.
Yes.
Mass
Over.
Times acceleration.
Yeah.
Yep. F equals ma. F equals ma. This, you memorize this right now. This is not that hard. F equals ma. Memorize it right now. But this relates force to mass and acceleration. Acceleration and net force are proportional and act in the same direction. Mass and acceleration are inversely proportional. So if the net force goes up, what happens to the acceleration?
Goes up.
It goes up, and that acceleration will be in what direction?
The same direction.
The same direction as the net force. If the mass increases and the force doesn't change, what happens to the acceleration?
It goes down.
It goes down. If the mass goes up, the acceleration goes down. They're inversely proportional. Excuse me. Your book, and I don't know why, I've seen other books do this too, but your book actually writes this equation as A equals F over M, which is true. You can see if we manipulate it, A equals F over M is also true. The reason I like this one more is there are two reasons. One, we're usually actually solving for force more often than acceleration. That's not always true, but in this text we actually are solving for force more often. But more importantly, this is much easier to manipulate. Anything that I want to get out of this, I can solve with one step. If I want A, I just divide M over. If I want M, I just divide A over. If I want F, it's already set up for F. Whereas if we have A equals F over M, which is what your book gives, we're going to have, when we're solving for mass, we're going to have a two-step manipulation to do if we do it correctly. Let's just do one of these real quick here. So force, mass, and acceleration. I want you to think about the way these things relate to each other conceptually as well. That means like picture this little word problem in your head and see how it would play out in real life. Because this is an intuitive thing that we realize. If I apply a net force, come here. This post stand, I'm always doing it to this stand. If I apply a net force to this stand, it's extremely intuitive that it's going to move in the same direction I apply the force. Wouldn't it be wild if I push on this stand and it goes the other direction? I would be very alarmed. I'd be like, the thing is haunted, right? It would have to be supernatural for this to not occur, right? In nature, this is always true. If I push on it, it goes that way, if it goes at all. Also, if the mass of this is greater and I push on it, it's not going to change its motion as quickly. Remember, acceleration, remind yourself, acceleration is not how fast something is going, it's how much its motion is changing. So here's as a little, side note, side note.
You have to put the box in.
I'm going to put the box, just give me a second. Side note, if I have Superman, ooh, good, this is a good one. Superman, who's blue, right? With a red cape. Is that right, or is he red with a blue cape? I don't care.
Blue with
Okay,
red cape.
Superman is stopping a speeding locomotive.
A speeding locomotive.
Hey, Justice, if you're going to be mean to me, then I'm going to be mean to you.
I'm not being mean.
Okay, good. That's what I
Look
thought.
at that beautiful train.
This is called a locomotive, actually.
That
Okay,
is not
so let's say that in instance 1 of our cartoon panel, the locomotive has this we'll just call this, this is a velocity, okay? It has a constant velocity in this direction. And Superman is going to apply a force. What? Just by the way I drew it, what direction does it look like Superman's going to apply a force?
Yeah.
Yeah, to the left of this. So he's going to apply a force in this way. So which way, according to Newton's second law, which way will the train accelerate?
Backwards, be super.
Yeah. It will accelerate this direction. So it'll have a negative acceleration, won't it? And negative acceleration means what? Do you remember this from the last
It
chapter?
go backwards.
No. Acceleration is not motion. It's not going to be moving backwards. What's going to happen? A negative acceleration means it's doing what?
Slowing down.
Slowing down. So if we apply a force to something that's already moving, the acceleration goes in the same direction as the force, but that doesn't always mean the motion goes in the same direction as the force. Are you with me? So in my what's this thing? Stool. In my stool example, if it's already moving this way, pretend it's already moving on its own. It's haunted. Okay, remember it's haunted? Pretend it's moving on its own, and I put a force on it going this way. Does that mean it's instantly going to go the other direction? No. First it has to slow down. Force relates to acceleration, which does change velocity, but it's not the same thing as velocity. Aye.
Yeah.
Justice.
What is that word after proportional and? It looks like
Act.
alt word. Put.
Act.
Personally, and all.
Anyway, so now we're going to do an acceleration. Let's just use this as our problem too. So let's say
Train.
Superman, hombre super. Superman applies a force of 169,000 newtons to a train with a mass of what's a good mass for a train? 125,000 kilograms. What is the resulting acceleration?
Well,
What should I do first?
a bunch of civilians died and Superman wrecked
Thank you.
thousands of dollars worth.
Justice is talking louder than you, but you're right. So what should you say again?
Superman
Write down the equation, or tell me what equation to write.
F equals MA.
F equals MA. Well, hold up, Tiana. The force was given to me in the equation. Why do I write it like this?
Raw equation.
You always write it like this to start out with. This is the raw equation. F equals MA. This is the one you memorize. Don't memorize the manipulations. Memorize this and then manipulate when you need it. What are we trying to solve for here? Acceleration. So how do I get acceleration by itself?
You divide M.
F over M. Oh, sorry. This whole time the F should have an arrow over because it is also a vector quantity. Please forgive me. The force is also a vector quantity. F over M equals A. Okay. What do I do next? Substitute. What's my force?
Your force is 169,000 newtons.
Newtons. My mass?
125,000. Yeah.
125,000 kilograms. Now, listen, what's going to go on with these units? You remember what we talked about? A Newton is equal to what? Do you remember?
120.
A Newton is equal to, I don't know if I actually told you this, but a Newton is equal to, this unit is equal to a kilogram meter per second squared. This actually comes from this equation. See, if we have mass, which is measured in kilograms, and we have acceleration measured in meters per second squared, that measures force. We abbreviate this whole lump here with the letter N, which is a Newton. So 1 Newton is equal to this. You should write that down too. Did you write it down?
What?
I had just got done telling physics last week, is probably why I thought I told you. But a Newton, the unit Newton, which measures force, is equal to a kilogram times a meter per second squared. And you can remember this because F equals MA. Mass is measured in kilograms, acceleration is measured in meters per second squared. So what will my unit be here? If I divide Newton by kilogram.
Yeah. I don't know.
Yes, meters per second squared. My answer is going to be in meters per second squared. Which measures what? What is this a measure of? Acceleration. So it all lines up, right? It all lines up. What is the arithmetic answer for this? We got this. We got the unit, which is the important part.
1.352.
1.352. And in what direction? If we're going off of this diagram, it'll be left.
Yeah.
the question itself didn't actually say what direction the force was, but we have to be careful to say that the acceleration is in the same direction as the force. And so if we were going off this diagram, which was kind of my intention, then the acceleration will be left and the train will be slowing down at a rate of 1.352 meters per second. Give me 1 second, Peter. Now what if as a bonus, what if we knew the velocity of the train? Could we calculate how long it would take Superman to stop the train? Yeah, we would use the A equals delta V over T. If we didn't know the velocity of the train, this question that I just made up didn't ask us to do that, but we could easily find time given this acceleration that we calculated and the velocity that we would have been given. Hayden.
Okay, so not to hold this background
No,
in
you're
here,
fine.
but is there any other way to have negative acceleration other than slowing down?
It depends. We talked about this. I can't remember if it was you or if it was in physics class, but I talked about this with some group of students. Depending on how we're defining negative, usually in just the normal way, negative acceleration means slowing down because it's relative to the original velocity. But if, for instance, if you have a reference direction, like if you're saying east is positive and west is negative all the time, and then you have a little dot and it's moving west, you would call this a negative acceleration also, even if it was speeding up, if you had a reference direction. Normally, in everything that I've seen, at least at this level of what we call classical physics, negative acceleration just means slowing down. It's just relative to the original velocity.
Okay.
If you find something online that tells you that that's not true, I would like to hear about it. But this is how I've always done it. This is how your book does it. Do you have another question, Pete?
Yes. Yesterday you told me you were going to grade the lab today. I just wanted to remind you.
Yeah, I will, if you shared it with me. Anyway, so we have Newton's first and second laws here. Do you have questions about Newton's second law? What was the one word we used to describe Newton's first law?
Inertia.
Inertia. What's the equation we used to describe Newton's second law?
F equals MA.
Does everyone have F equals ma memorized? Raise your hand if you've memorized F equals ma and what it means. Okay, you're going to keep memorizing it, okay? If you haven't, that's okay. Just make sure you get it memorized before the test. I hope it's clear to you. It's not just about the test, but this is important in real life. This is how the world be, fellas. This is how it is. This is what it do. Okay, let's move on to the next thing we're going to talk about is friction. So please label this section of your notes. Friction.
Question.
Yeah, but
What?
yes.
Are we actually gonna have that camel question in the next test?
Just the last one.
You forgot to put in the last one.
I never forget. No, that's not true. I almost always forget. What? What are we talking about?
The camel question.
Yeah.
Nathan.
Write down friction. I'm going to leave the major heading, which is Newton's second and third law. This is still, I would consider it part of Newton's second law. Newton's second law isn't about friction, but we talk about friction a lot along with. Hey, why are you guys talking? Let's be quiet and listen, unless you have something to add to the discussion, which I don't think you do. Friction. To give me a layman's definition of friction, not from your book, just tell me what you think about friction. What is it? Yeah, Tiana's doing the hand rub thing. We know about friction from the time we're little babies. It generates warmth. Yes, Colton.
So, two objects catching on each other and rubbing.
Yeah. Okay, so it has to do with a rubbing. In fact, if I remember correctly, the Latin word from which which might be fricasse. I don't know. That sounds Italian, but I think it means to rub. That can be we use this allegorically all the time. If I say that there is friction between Mr. O and I, what is that probably?
Like there's
Like
bad
fighting.
blood.
Yeah, like some bad blood. That's another allegory. But yeah, we probably don't get along. It's not true, or at least I don't think it is. At least not from my end. Ask them about it later, but I don't think it's true. But it just means someone, maybe we could even say, rubs you the wrong way, right? If you rub a cat the wrong way, it don't like that. You know what I mean? Like the dog does not care. The dog is like, yeah, thanks for touching me. I don't care what you do. But the cat is like,
I'll bite you.
but yeah, friction, I'm pretty sure comes from the Latin. Look it up on your own later, and if I'm wrong, I'll give you a bonus point if you can show me that. But I think it relates to the Latin word for rubbing. Don't do it now, Cyrus. I specifically told you later. Anyway, friction is when, I like what Colton said, they catch on each other, because even if something is smooth, even if it's smooth, nothing in the universe is perfectly smooth. Everything is made of what we call micro ridges. So even this whiteboard, we'll say it looks like that, and we'll say that the eraser has some even deeper, it's all like furry and like that. These are two surfaces. What must be happening for these two surfaces to generate friction? They must be,
Rubbing against each other.
yeah, we'll say that they must be in contact. Friction only occurs when objects are in contact. Friction only occurs when objects are in contact.
Question.
Yes.
Do we write the weird wave thing?
Yeah.
Okay.
Your notes, but I would if I was taking these notes. They must be in contact. Friction kind of works in two ways. There's such a thing as static friction, and then a lot of times people will differentiate these into rolling or sliding friction. Sometimes we might call it dynamic friction, maybe kinetic friction. But static friction is what exists. So this has a magnet in it, so don't really. This is not a good example. But if I do the same thing with this little fuzzy eraser, I don't actually want to touch it because it's all gel. But if I do the same thing with a fuzzy eraser, this one's probably even worse. And we'll say that my book is the example now. Look at this. It's a relatively smooth book. It still has ridges, but my fuzzy eraser is on it. If I put a tiny bit of force in it, which I am, and it's actually moving. But if I put a tiny bit of force in it, it's not going to move. The friction. This is the friction. Static friction is the friction. Well, let's not use the word to define the word. It's the force preventing
Movement.
Yeah, movement.
So Mr. Time.
Or let's actually write it this way. A force preventing change
In motion.
in motion. A force preventing acceleration. We say it, I say it that way, because this force is counteracting the force I'm putting on it, so the net force is zero. This is the force preventing a change in motion. The rolling or sliding friction would be a force preventing the, let's put continuation of motion. This is the reason that Newton's first law sometimes seems wonky to us, because Newton's first law says that if an object is in motion, it'll stay in motion, implying infinity. But if I roll a ball or slide this across the floor, what will happen in the real world?
The force will actually.
It'll stop. It'll slow down and stop, and then we think, I'm smarter than Isaac Newton. I disproved Newton's first law. But did you really? No, because there is an unbalanced force. It's just that unbalanced force is provided by friction. The unbalanced force is provided by friction. So where could we go? Where could we go to test if Newton's first law is actually true?
What's that question?
What's that bottom word?
Motion.
What's the top word about that one?
To the deep corners
Oh.
of space where air resistance is.
Yes, to the deep space where there is no friction, because there's no touching, because there ain't nothing to touch. Not nothing. There's roughly, I don't know, something on the order of 10 to 100 atoms per cubic meter. So eventually, even in space, if you're going fast enough, the friction will catch up.
Probably like a rock or something. I don't know.
But if we were in outer space and there was barely anything to be in contact with, there would be no friction, and so an object would move in a straight line forever. Almost forever. If there was literally nothing in space, then we move in a straight line forever. Forever. There's another kind of, I don't know, we're going to put like a half box here. These are the two main types of friction, and really this last one is a type of this. But we can also have something called fluid friction, which we a lot of times will refer to as air resistance. Obviously, fluid friction is a more incorporative term than air resistance. What else would fluid friction involve that air resistance doesn't?
Water.
Yeah, the liquids. So any kind of fluid can impart fluid friction, but air resistance is one type, and this prevents or slows, I'll just say that's not great, but slows motion in a fluid. This is why an object in flight will eventually also fall. Gravity comes into play here too. Do you have questions about any of this, about friction? It's the same thing. Oh, something kind of interesting that causes friction to occur is that what's really happening on the atomic level is that little molecular bonds are being formed and broken every single time. So it's actually, there's a bond forming between the parts of this. That's also how glue works. Anyway, you have questions about friction?
Nope.
You're going to have an assignment. You only got through lesson 1 instead of all 3 of the lessons, but that's okay. Do you have any questions?
Yeah.
You're